Right. You can you see that spreadsheet file now?
Yeah.
Yeah. So looking at that, this is the problem of the heights of people. So in this column here, we've got our class midpoint. So these are bottom class, top of class. The class midpoint is B3, which is this one, plus this one, and divided by 2. And then you put your frequency data in here. And then this one is going to be the class frequency E to E3 times the midpoint D3. D3 times D3. Yeah. And that was, I managed to do that quite quickly because I copied this sheet from the problem this morning and checked everything and changed the data, and straight away got the answer to the problem, because the mean is F9, which is this one, sum of this column, and that's divided by E9, which is the sum of the class frequency. Yeah. Okay. So that gives you, and I think even if you were doing these by using a calculator, you're probably best to build up a table like we've got here and calculate each of these columns. And
yeah, I did that. I did the calculator. Yeah.
Even if you're not doing a spreadsheet, a quick table like that is probably the easiest way to make sure you've got everything, got it all right. Yeah. And then when you want to add the standard deviation to the problem, which is the last problem in the notes this week, you've got the extra 3 columns added. So this column here is X minus X bar. Well, the mean is X bar. So in that column, we've got D3, which is the mid-class value, and that's divided by E12, which is the mean. And then in this column, we're going to square this G column. So it's just G3 raised to the power of 2. So you do that in Excel. Okay. And then lastly, we're going to multiply everything in this column by the relevant class frequency. So this one is H3 times E3. We then sum up all the frequency column, we get 100. We sum up all this column here to get the 8,225, and then this formula here is the square root of I9 divided by E9 to give us a standard deviation. And I put the formulas in there as well so that you can see. So this is the formula. This is effectively the full formula for what's in there. But a lot of that calculation has gone on within these columns here. Yeah, everybody understand that?
Yeah.
All right. So what I'll do is I'll send that spreadsheet out with the solutions, the normal solutions file to the exercises for this session or last session. All right. Everybody happy with that? And I've covered that. Is there anything else you want me to do on this morning's session before I move on to probability?
No, I'm good.
Everybody else good?
All good for me, mate.
Yeah. Okay.
Yeah,
I'll stop that share, and we'll move on to the next bit. Right. So share content, screen, start broadcast. Right, here we go then. Probability. Okay, so what we're going to do in this session is an introduction to the terms used for probability. We're going to look at some laws of probability. Then we're going to look at some works problems involving probability, and then we're going to look at something called binomial expansion by Pascal's triangle. Okay, so that sounds a bit fancy, but actually that's not too bad once you realize the purpose of it. Okay, so that will enable us to do probability across multiple items. So first of all, the introduction to the terms. So probability. And the probability of something happening is the likelihood of it happening. Values of probability will always lie between the value 0, which is absolutely can't happen, ever, never, and 1, which is a certainty. We'd all like that in the 6 o'clock at Haydock Park. A certainty. We won't have to work anymore. So those ones don't turn up very often, but there are some examples you could come up with. So 0 represents absolute impossibility, 1 represents an absolute certainty, and there's some examples there. The probability that a length of wire has 0 resistance at 100 degrees C is an absolute improbability, so its probability is 0. That a fair 6-sided dice will stop with a 3 upwards is a 6, or 0.1667, because there's 6 numbers on the dice, 3 is just one of them. That a fair coin will land with a head upwards is a half, or 0.5, and the length of copper wire has some resistance at 100 degrees C. Well, that's a certainty. It will have some. Okay. Then they tend to use P as being the probability that something will happen, and Q is the probability that the same event will not happen. Those two probabilities, if there's only 2 choices, always add up to 1. I have to, yeah? So P plus Q is always 1. Yeah, equally, from that, Q is 1 minus P, and P is 1 minus Q. Yeah. So the fact that you know they always add up to the whole, if you know one of them, you can always find the other one. Yeah. And consequently, you should realize that P and Q are always a number between 0 and 1. They're always less than 1. Yeah. Okay, everyone happy with that?
All good.
Good. Right, expectation, E, of an event happening is defined in general terms as the product of the probability P of an event happening and the number of attempts made, N. So E is equal to P times N, where N is the probability of the event happening and N is the number of tries. So since the probability of obtaining a 3 upwards when rolling a dice is 1/6, the expectation of getting a 3 if we do 4 throws is a 6 times 4, which is 4/6, which simplifies to 2/3. So if you're going to throw the dice 4 times, the probability that you'll get at least 1 3 is 2/3. Yeah. Everybody happy with that?
Yep.
Good. Dependent event. A dependent event is one in which the probability of an event happening affects the probability of another event happening. For example, if 5 transistors are removed at random from a batch of 100 for testing purposes, and the probability of transformer being faulty, P1 is determined. If at some time later, a further 5 transistors are taken randomly from the remaining 95 transistors, and the probability of faulty transistor is again calculated, P2, the probability P2 differs from P1 because the batch size has changed. This means that P2 is dependent on the probability P1 because of those initially 5 transistors being removed before the second 5 were removed. For this reason, the second random selection is said to be without replacement because you haven't replaced the transistors you took from the sample. Yeah. So that's the second event is probability is dependent upon the first probability. Independent event is one in which the probability of an event happening does not affect the probability of another event happening. If we take a similar example, 5 transistors are removed at random from the batch of 500 and calculate the first probability P1, just like we did before, but at this time, at some time later, the 5 removed resistors are replaced before randomly selecting a new sample. Then we get a second probability P2, and the probability P2 is equal to P1 in the sense that they're not affected by each other. So since the 5 transistors are replaced between the random draws, the second selection is said to be with replacement. So that's the difference between a dependent event and an independent event. If the sample changes, then one is dependent on the other. If you make the sample size the same, then they're independent. Again, everybody okay with that?
Yep. Good.
Yep. All right, Ashley, yeah? Solly?
Yep.
Make sure you speak up if you don't understand. Okay, now we move on to conditional probability. It's concerned with the probability of, say, event B occurring, given that event A has already taken place. So if A and B are independent events, then the fact that event A has already happened will not affect the probability of event B. If A and B are dependent events, then the fact that event A has already happened will affect the probability of event B. So this depends on whether you have independent or dependent results as to whether there's a conditional probability. All right. If you think about it, the chances of getting 3 6s from rolls of dice in a row depends on you getting 2 in a row first. Yeah. So that's the best example I can think of off the top of my head. What we're going to do now, and this is where concentration really needs to start, okay, because it can get a little confusing. But we'll try our best. Laws of probability. The addition law of probability is recognized by the word or joining the probabilities. So if a probability event A is PA and the probability event B is PB, the probability of event A or event B happening is the probability of A plus the probability of B, provided the 2 events A and B are mutually exclusive, i.e. they can't both happen. So on a single roll of a dice, you can't throw both 1 and 6 at the same time, but the probability of throwing a 1 or a 6 is that it is the probability of the 1 added to the probability of the 6. So in the sense of that, we know that throwing a particular number on a dice, the chance of throwing a 1 is a 6, chance of throwing a 6 is another 6. So the probability of 1 or 6 is equal to 2/6 or a third. Yeah. Similarly, if there are 3 or more exclusive events, then the probability of one or other of them happening is all of them added together. So taking that dice thing, the probability of you getting any number between 1 and 6 is all the 6 added together as 1. Yeah. So as long as all these events are completely independent of each other, and you can't get both of them, any 2 of them happening at the same time, the probability of one or the other is to add them together. Yep. Everybody happy with that?
Yeah, can you just give me 30 seconds just to write down this last little bit?
Yep.